Okay, I welcome all of you into today's interaction. And today, actually, we'll be talking about one of the principles in the physics that tells you no, that tells you. I think this is the only principle in physics which is negative in sense. It's the negative principle. It tells you that you cannot do it. So we want to realize this, what we call as Heisenberg's uncertainty principle. And to move on, what I was talking about, I was talking about the negative principle that we have in physics. Okay, this is the only argument that's negative, and the negativity of this principle is giving basically the stability to an atom, and we will realize it in a moment. So before we proceed in, I would again like to go back to the classical physics, and I would come up with an argument. Say, for example, if I know at this moment of time the position and the velocity of the planet, okay, if I know these two things, the position and the velocity with which the planet is moving, classical physics can predict what will be its position and what will be its velocity after 1 year. Right? So here you are having a complete deterministic approach. You can accurately predict the future, and you can accurately predict the present. Now, when we go into the domain of atoms and molecules, if I try to look towards an electron, if I try to see the electron, if I try to locate the position of an electron accurately, I can less accurately calculate its velocity, and the vice versa. So if I can more accurately calculate the velocity of the electron, at the same time, I cannot accurately measure the position of this electron. This is the argument that's given by Werner Heisenberg in 1927. And the argument is that there are certain pairs of physical quantities. This is not universal. It is not true for all physical quantities. It's true for some physical quantities where you cannot accurately measure both position and momentum of the particle, of the microscopic particle. Now, the point here is the fault lie with the measurement that you are making on this argument? No. That's not the reality. The reality is that the nature is behaving like this. The universe does not have anything by virtue of which you can measure both position and the velocity of this microscopic particle. Now, to move on from here, let's first try to realize the position and momentum relation that we have. As we know what Heisenberg's uncertainty principle is, delta x, delta p is greater or equal to h bar by 2, where h bar is the reduced Planck's constant, and delta x is the uncertainty in the measurement of the position, and the delta p is the uncertainty in the measurement of its momentum. Now, if we assume that we have a quantum mechanical microscope, okay, and let me choose a character. Say the character A is interested. He wants to do an experiment, and he wants to measure the position and momentum, and his target is that he wants to measure them both at the same time. This is the target of this boy, say the boy A. Now, there's a particle, it's a microscopic particle, and the boy has to see this particle. How can the boy see this particle? To see the particle, you want this particle to be localized. You want this particle to be measured. You want that the position of this particle to be measured. So how can you measure it? You can measure it when you can see it. You want to see it first. So if you want to see it first, what you need the light. And what light is? Light is something made of photons. So photon is a particle, right? Now, to locate the particle, what you do? You use a photon of short wavelength, right? Short wavelength means what? E equals hc by lambda. If lambda is large, the energy is small. If lambda is small, the energy is large. So when you do it, what you are doing? To see the particle, you are disturbing the momentum of the particle at the same time. So using a low wavelength photon, you are using a high energetic photon, and if you are if you are looking at this particle accurately, more precisely, you are disturbing the momentum of the particle. And he tries to do this measurement many ways. But every time the measurement is done, you are able to measure one thing precisely, more precisely, and at the same time, the other thing is measured less precisely. So this gives us the complementary relation between the position and the momentum of this particle. Now we have another equation. What is that? Delta E delta T is greater or equal to h bar by 2. Now to realize this relation, let us assume there is a boy A, and his target is basically to calculate the energy of a photon. What he does, he takes a hypothetical box and he puts just one photon in that box. This box has the walls, and all the walls are reflecting. They are perfectly reflecting. So the photon is inside the box. Now the boy A, the box has a small door. The boy A opens the door for the short time. So opening the door for the short time, the boy wants to see the photon coming out of the box. And keeping it for shorter time, opening, say it opens the door for a millionth of a second. So what's going on? The measurement of time, the time is very small. The uncertainty in the measurement of time is small, but the uncertainty in the measurement of the energy of the particle is large. So when he detects the energy of the particle, the energy happens to be either greater than that of its original energy, or it happens to be less than that of its original energy. So some kind of dance is happening. The true nature of the particle is not predicted completely. So what you measure is more or less. Now this boy A repeats the experiment. He opens the door for many seconds. When he opens the door for many seconds, the energy that he calculates is more precise. But the time, he is not sure at what time the particle will leave the door. So there is more uncertainty in the measurement of the time. So this is how we realize the complementary nature of these physical quantities. If you measure precisely the position of the particle, then the nature will react to you in such a way that you will not be able to measure the momentum of the particle at the same point of time. And the story is same for energy time, and the story is same for angular momentum and angle. So, what are its implications? The very first implication of the Heisenberg's uncertainty principle is, suppose you have an atom and an electron is revolving around the nucleus of this atom. If you will be able to locate electron 100%, the electron will have infinite momentum, the electron will have infinite energy. The atom will collapse. So the principle that we call as negative principle of the physics, it is giving you an explanation that why an atom is stable. Electron roaming. And if you are able to locate it 100%, it will have infinite momentum. It will have infinite energy. You will not have the stability of an atom. There is another implication of Heisenberg's uncertainty principle, and that's the creation and annihilation of the particles. The classical physics says vacuum. What is vacuum? Classically, when I say vacuum, you mean nothing. You mean there is no particle in that part of the space. But quantum mechanically, what we say vacuum is not something that there doesn't exist anything. Every time there is creation and annihilation of virtual particles. And what is happening? The nature is behaving like this. The uncertainty principle prohibits us to detect these virtual particles. This is the basis of the quantum field theory. So this is how this uncertainty principle becomes so important. Now, if I rightly talk about the man that I have, there are two people, they seem to be twins. I don't want to talk about them. Einstein never believed in those kinds of probabilities. And uncertainty principle is the backbone of the quantum mechanics. Because the argument of the Einstein was what? God does not play the dice. And Bohr answers this argument. And what is the answer? And what is the answer that's given by this genius? God does not tell you what to do. God does what he has to do. So this is how the beauty of uncertainty principle goes on. So let us talk about this principle and let us demonstrate this mathematically. What should I do it now? How should I close it? I have closed it. Okay. So now what we have? We have the uncertainty in the measurement of the position, and if I represent that uncertainty as delta x. So if delta x is the uncertainty in the measurement of the position, and delta P is the uncertainty in the measurement of momentum. So in one case you have position, and in another case you have momentum. And the uncertainty principle tells us that the product of the two, delta x and delta p, is always greater or equal to h bar by 2. Right? Now, how to realize it? And before proceeding, now, what is this delta x? This delta x is basically the standard deviation. It's the standard deviation. That will be the right way of talking about it. And the standard deviation of the position can be given by under root of x squared minus x squared. And what is delta P? Delta P is the standard deviation in the momentum. And that standard deviation is P squared minus P squared. So these are statistical calculations in the original hypothetical experiment. Now, see what I have? I have uncertainty in the measurement of the position. I want to see the position of the electron. And I want to measure the momentum of the electron at the same point of time. Right. Now, what does that mean? What we have basically, I can think of, say, a distribution of position. Say, psi of x. So you have a distribution of positions, x0, x1, x2, and so on and so forth. And you have a distribution of, you have a distribution of momentum, psi of p. So P0, P1, P2, and so on and so forth. So here you have the distribution of the position, and you better understand that you can calculate the probabilities by taking the complex conjugate of these functions. Now you are dealing with the position space, and you are dealing with the momentum space. And you can connect the two. You can connect the two situations. You can connect position with the momentum with a very fundamental, strong tool that we have, and that's Fourier transform. Right? It's the Fourier transform that can take us from the position space to the momentum space, from the momentum space to the position space. Right? Getting? Okay. So if I have to write down the psi of x. Now what is psi of x? It's the position. We can write it as the superposition, the continuous superposition of the positions. And for continuity, what we use in mathematics is integration. Isn't it? What we use? Integration. So I will not be using the normalized constants. For that, I'm going to share the video on the actual mathematical formalism that you have. Okay, you will see that and you will work on that. So I'll be just using the peripheral things. So psi of x So it can be written as minus infinity to infinity psi of p, and the combination of some say cos of px and dp. Okay, so this is psi of x, and I can write down the Fourier transform of it. I can write down psi of p as integral minus infinity to infinity psi of x cos of px and dx. Right? And you can see how we track down those quantities. You can see that, you can check that. Now the point is for a particle, psi of x equals e to the power of minus alpha x squared, and psi of p comes out to be e to the power of minus p squared by alpha. This is the core idea of uncertainty principle in the framework of its mathematical modeling. Here you are in the position world, here you are in the momentum world, and between these two equations there is a common thing in the right hand side. What's that common thing? What do you find in these equations that's same in the right hand side, that looks same? It's alpha, right? Here the alpha is here, and here the alpha is in the denominator. The alpha has inverse relations, and you understand the inverse relations. If one thing is large, the another thing is small. If one thing is small, the another thing is large. So if I interpret this thing graphically, what does it mean? It means in a position space, if I have this as, it's looking bad, okay, anyway I'm trying it. If this is psi x, this will be your psi of p. See, here the position is very, very localized, and at the same time the momentum is weird. The momentum is distributed over the large distance. So that means there's a chaos for the momentum in the momentum space, and the vice versa. And this thing is the result of what? It's the result of that exponential. In the exponential of the position, alpha is multiplied. In the exponential of the momentum, it is 1 by alpha. And this is your Gaussian distribution. And you can see in the position space, you can localize your situation. There is that much delocalization in the momentum space. And the vice versa. This is how we can understand the uncertainty principle in mathematical sense, right? And there are other simple applications of this principle. You have already gone through them. Like uncertainty principle tells you that electron cannot exist inside the nucleus. You can do that calculation within the framework of the size of the nucleus, and you will find the result. The result will dictate you that electron cannot exist inside the electron cannot exist inside the nucleus. And there is another important application of uncertainty principle, that is that it tells you that that these quantum mechanical particles can have energy even at absolute zero. Absolute zero. What is absolute zero? It's 0 Kelvin, right? So classically, anything that you will have at absolute zero will cease to have any energy, it will have zero energy. Even though we understand classically that we cannot achieve the 0 Kelvin temperature. But if we achieve 0 Kelvin temperature, what's going to happen? The motion will cease, it will have zero energy. But Heisenberg's uncertainty principle will, if you emulate it on the problem, you will calculate the energy that's called as 0-point energy of the harmonic oscillator when you choose that ideal harmonic oscillator in place, right? So anything, any kind of interaction will have any kind of thing. No? Nothing? Okay.